following Foppian form. It's got, so let me show you how I get it. This is not yet the Foppian form. I got dy is equal to f of, x comma y dx. And that implies that f of x comma y dx minus dy equals to 0. There you go. This is a Foppian form. Of, I need to give it a name. I haven't used ghost in a while. I'm going to call it ghost. There. I'm sorry, this ghost is not exciting enough for me. Give it some. There. Sorry. You guys paid good money for this class. I should give you, high resolution ghosts. Any question? I mean, this is just terminology, but the point is you can always take that differential equation and rewrite it in this dx dy kind of format. Listen, the advantage of the Foppian form way of thinking is that it doesn't say x or y is special. X and y are treated on an equal footing, right? So in some, the explicit solution viewpoint is very limiting because you're stuck with all of the baggage of looking at graphs of functions. What are graphs of functions have to do? They have to pass the vertical line test. Do level curves have to pass the vertical line test? No. Are there interesting level curves that are not functions, graphs of functions? Oh, yes. Most everything you're interested in engineering and physics is not a function graphically, right? Circles. Equipotential lines. These are closed loops, typically, that, right? They're not a graph of a function. They are a level curve, though. So and the implicit solution viewpoint is a useful one, is my point. So, usually, day one, if you watch the last 3 or 4 times I've taped this class, because it's just so very exciting to go back and watch the first class of other years, right? I'm sure you're all doing that. But what I typically do, if you watch me, I'm a creature of habit, I'll say a bunch of jibber-jabber about independent and dependent variables. I'll regret spending too long on it. At some point, I'll start talking about how to solve first-order differential equations, at which point I'll fess up that there are 3 methods, and then I'll say, oh, wait a minute, no, actually there are 4. And so this is, I'm saying those things now. So the 3 methods to solve dy dx equals to, you're like, this is a very meta year of differential equations. In some sense, yes. So here's the 3 methods, and you've already seen 2 of them. Separation of variables. The other is exact equations. And here's the one we haven't touched on yet, but you should have seen in Calculus 2, is the integrating factor technique. Integrating factor technique. And then there is a 4th, less pleasant thing, which is substitution. Substitution, that's really just my label for a maelstrom of other methods, which involve clever introduction of new variables to change the given problem into one of these 3 things. All right. This story should sound familiar to you. This is the story of integration, right? We learn a few simple techniques, and then we learn substitutions to contort things back into those basic cases, right? Separation of variables, I think everybody can do this, right? So when can you do separation of variables? Something like this says, hey, I can be separated, right? So we separate. Separate, integrate, right? this is a good chance for me to point out, I could put a box around it. At this point, I have found the what solution? The general implicit solution. Now, is it really general? Not entirely. What is missing from the red boxed equation? What's that? No, the constant's there. I got a constant. Look, I got a constant. Oh, but the general solution, the idea of the general solution is, by different choices of the constant in the general solution, we can cover all possible initial conditions, right? So for it to be the genuine general solution, it should cover all contingencies for the differential equation. Does this cover all contingencies? Is there a solution which is not included in here, in this formula? And my second question to you is, why did we miss it? Natural log of a negative number. Oh, good point. But I do have, I know it's a little, yeah, I have absolute value. I think that's not the problem, but you're getting closer to the problem. What's involved in going from this step to this step? What did we do? Yeah, we divided by y, which means y couldn't be 0. So how do you decide whether or not 0 is a solution? Go back to the start. Does it work? If I plug in y is identically 0, the constant 0 function, is that a solution? Is the derivative of the zero function 0? Yep. I mean, derivative of any constant function 0. How about x times the 0 function? Is it 0? Yeah. So 0 equals 0. Plug it in. It works. Y equals 0 is another solution. That's called so y equals to 0. And if I write 3 equals, that just means it's identically equal to 0. I'm saying it's the 0 function is an extraneous solution here. You guys know what an extraneous... So, I mean, for example, I often will say that if I was to be a rapper, I've thought about this, I would be extraneous G, and then I would be like, my tagline would be like, I'm not even in the solution set. So, thought about this. So extraneous means it's, it's outside the solution. It's a special case. So, yes. So you see, extraneous G, that would be it's good. What? I have the life experience to say it. Don't judge me. See here. Exact equations. Is this an exact equation? I don't know yet. See, to figure out if it's an exact equation or not, I would take this and I would write it in its Foppian form. What's the Foppian form here? Well, how about x, y, dx minus dy equals to 0? If I take this differential equation and I try to look at it as an exact equation, is it exact? Do the coefficient functions, x, y, and minus 1, correspond to the component functions of a conservative vector field in the plane? They do not, because if this is my p, my q is minus 1, right? And partial p, partial y is x, which is not equal to 0, which is, by the way, partial q, partial x. This equation is not exact, but it is separable. Listen, these are not mutually exclusive methods. There is interconnection. Sometimes you can do one, sometimes you can do the other. The integrating factor technique is specifically designed to solve the following problem. dy dx plus py is equal to q, where q and p are functions of x alone. I would ask you the question, is this linear differential equation, which, by the way, is in standard form, copyright, is that an exact equation? Well, I don't know yet. I mean, put it in its Foppian form. See what happens. Can you guys, you guys work that out? What's the Foppian form of that linear differential equation? You guys work it out. So what do we got? We got ourselves a q minus py dx, right? Minus dy equal to 0. So what happened? This is, oh, unfortunate. I better use my mn notation, right? This is m, and n is equal to minus 1. So what's partial m? What's partial m partial y? See, q is a function of x, p is a function of x, y is y. So this is 0, and this just gives me minus p. What's partial n partial x? It's 0, right? So if the coefficient function p is non-zero, it's inexact. It's not an exact equation. But here's the neat thing. Fops theorem says something kind of shocking. It says that there exists I such that Im dx plus In dy equal to 0 is exact. There, of course, is some fine print to whether or not that I exists, but it's relatively benign. I is called the integrating factor. All right? So what I'm saying is that we could multiply this equation, for example, let me call it star, multiply by I q minus py dx minus I dy. If we multiply by, there's some I, we could make up some I that when we multiply like that, it becomes an exact equation, right? So this would be the new quote-unquote m. This would be the new quote-unquote n, right? Now, when we're solving differential equations, something we can always do is we can add conditions to the thing we're looking for, right? It's like if you're looking for a mate, you could say, I want to marry someone who is very interested in Star Wars Legos, but just does not care for Lord of the Rings Legos. And you could just like be dogmatic about that. Now that might be too strong a condition. You might have to give up on that and like look for other people. But at least at the start, you could try for just a Star Wars Lego person, right? I mean, for example. So here, we could say we're just going to let I equal to a function of x alone. And if you do that, what does partial m partial x look like, partial m partial y look like? It's just minus ip. And what's partial n partial x look like? It's minus partial I partial x, which is minus di dx. And so you see the condition that you need is that di dx is equal to ip. Now di dx equals to ip, you can separate and integrate that equation. That's actually di over I equals to p dx. Integrate both sides. Whoop, 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 whoop. We get the natural log of the absolute value of the integrating factor is equal to the integral of p dx. We can't do that integral because we don't know what p is. And lo and behold, we find that the integrating factor is the exponential of the integral of p dx. That is the integrating factor you should have been taught in Calc 2. That's what you multiply the differential equation in order to be able to solve it by the reverse chain rule. I mean, reverse product rule. Now, if you didn't see that in Calculus 2, that's okay. We're going to cover it again in here. But I just wanted to connect the dots here and show some connection between things. But that's actually a derivation of the integrating factor, which I will, a separate day, show you how to use it and solve problems, right? So, anyway, next time, I will talk to you guys a little bit about something called differential forms. It will give us a new appreciation for this closed condition, and I'll make good on some other promises I did, like showing you that topological defect, why when we drop simply connected, things change. So, thanks, guys. We do end at 12:30, right? Yeah. Okay, and it's just 12:31, so I guess I need to let you go early next time, right? Yes. Okay. I mean, if there are no objections.